So here's what we have to do. We have one last what we'll say one last application of the derivative, and then we're going to move on. And this application is called L'Hopital's rule. So this reads, the way you say this is low P tall. That's one way to say it. Phonetically. So this is related to the tangent line in this linear approximation. So what this does is this is a sort of it's sort of like a shortcut. So not a shortcut, but in many ways it's a workaround. So this theorem, and it is a theorem, that's important to understand, will provide a useful method for computing many limits. So let's sort of motivate it with an example. So to motivate, let's consider this limit. The limit is x goes to 0 of e to the x minus 1 over x. So suppose I gave you this limit and I said compute this limit. Now hopefully the first thing you would do is you would try to plug in x equals 0. So the thing is you note a direct substitution of x equals 0 gives 0 over 0. So remember, when we're doing limits, the most sort of the best case scenario is that you can do this, that you can plug the value 0 in for x. So that is sort of the best case scenario, but we can't. And then the next thing to note is that it's also not clear how algebra and/or the squeeze theorem might help. So what I'm suggesting is what we know about limits at this point, what we've learned about limits and how to compute them. None of the tools that we have to this point are going to work. I mean, there's really no way to factor the numerator. So you can't cancel anything out like we've done in the past. And then it's really not obvious at all how the squeeze theorem might apply. So if we were to look at the graph, and we can do that right now, if we go to Desmos. And I graph this thing, it's going to look like there's a limit. So if I graph this, if I put my finger on the curve and I move towards x equals 0, it looks to me like there's a limit, and it actually looks like the limit is 1. So if I either put my finger on the curve, and by looking at the graph, looks like the limit's 1. If I did a table and computed some values like 0.1 and then so even if I decided to do some numerical experiments, it looks to me like there's a limit and it looks like 1. But the question is, how do we verify this? How do we use deductive reasoning? How do we use theoretical tools to know that in fact this is true? So here's an idea, and this is sort of the gist of why L'Hopital's rule works. So so here's an idea. When x is approximately 0, we know that e to the x is approximately, let me be a little more, even more specific. We know that e to the x minus 1 is approximately its linear approximation. So again, this is from the linear approximation stuff we did before. And so 2 classes ago, we showed the tangent line to e to the x was 1 plus x. Thus, we can say e to the x minus 1 is approximately 1 plus x minus 1, which of course is just x. So again, I'm using some hand waving reasoning. I'm using intuition. My intuition tells me that when x is close to 0, e to the x is close to its tangent line. And so what we can reason then, and again, we're not being very precise right now, but what we can reason is that we would then imagine that e to the x minus 1 over x would be approximately 1 plus x minus 1 over x, which of course simplifies to x over x, which is 1. And we would imagine this is true when x is approximately 0. Now, this is good news because what our sort of hand-waving reasoning shows us is that this limit should be 1. So what this suggests is the limit as x goes to 0 of e to the x minus 1 over x is 1, just like Desmos or the graph suggest. So the only thing we have to do, though, is make sure there's no loopholes in our reasoning. We have to make sure that our reasoning is sound and it's not just unique to this problem. So before I do that, does anybody have a comment or question? Way back there in La La Land? At least some of you are here. I'm not teaching to the wall. We still have to figure out where half the class disappeared to. The corona. So what L'Hopital's rule does is it is the theorem that tells us this is good reasoning. So the above reasoning is logically sound. Thanks to L'Hopital's rule, which we haven't stated yet. So what does L'Hopital's rule say? Well, we're not going to write it in its this very fancy specific realm. We're going to do it in a very calculus 1 manner, in hopes that it makes sense to you. So it says this: suppose the limit as x approaches a of some expression which I'll call f divided by another expression, suppose that equals 0 divided by 0, or this limit equals plus or minus infinity over plus or minus infinity. What is the result? What does L'Hopital's rule say? It says, then the limit as x approaches a of f of x over g of x actually is the same as the limit of the derivative of the numerator divided by the derivative of the denominator. So this is L'Hopital's rule. Now we want you to think about, why is this true? This is really the reasoning we used on the previous line. what this theorem says, what L'Hopital's rule says, is if this ratio, the limit has a form either 0 over 0, which we had, or infinity over infinity, pluses or minuses are irrelevant, then this limit is the same as the limit of the derivatives. Now, what we showed you in the previous problem is sort of a good intuition for why this is true. Because what this is saying is that in a function, when we zoom in small enough, really behaves like its derivative. I mean, think about that. That makes sense. We're basically saying when you're close enough to A, when you really zoom in and look at the inputs near A, the difference between the function and its tangent are really negligible. And that goes back to the theme I've said to you many, many times before. Take any curve you want. I don't care how curved it is. Zoom in, keep zooming in. Eventually, your curve is going to look like a straight line. That's just the way it is. You can't fight it. That's nature. All right, so let's look at it. Let's put our previous example in terms of this notation. And then we're going to explain to you again why this works, at least intuitively. So let's redo our example. So the limit as x approaches 0 of e to the x minus 1 over x by L'Hopital's rule. And by the way, it's usually nice to let the person who's reading your stuff know what you're using. I am going to differentiate the numerator, and I am going to differentiate the denominator. The numerator's derivative is e to the x. The denominator's is 1. You got a question?
I'm just trying to see.
Can you not see?
The greater than symbol. It took me a minute.
Greater than? No, this is not greater. This is an L.
Oh, okay.
Yeah. So that's a good. No, that's fine. You looked like you couldn't see. That's why I asked you. I didn't mean to pick on you.
No, my glasses
It looked to me like you're like, what the hell is right? So let me put that over there. It's important. So it is useful to put like an L with a circle, so the reader knows I'm like you guys getting everything messed up, that you are using L'Hopital. So that's an L. It's not a great. It's not an inequality. I'm sorry, that's sloppy. But look, here's the beauty of this. The beauty of this is, look at the limit we now have. The limit we now have, there's no bad news. I can now plug 0 in. I now get e to the 0 over 1, which is 1 over 1, which is 1, like we figured it would be. Any questions?
What do you forget to bring the L? Like, would you like take off max?
Oh, no. So I think the question you're asking is, if you didn't write this L here, would I take off points? No, probably not, but you should write it. It's important. Look, I know it doesn't mean much to you guys sitting here, because like I said, your math education to the point is just basically learn procedures, memorize them, repeat them. That's math to most humans on the planet until you get to the university level. But at some point, you need to transition to understanding why things are true, not just writing equations, not just writing symbols down, but being able to justify why this is true. It's not elementary that this and this are equal. Like, it's not elementary that this top line is an equation. And in fact, it's not always true. It's not always true that these derivatives, when you take their limit, it's equal to this. It's only true in the sense that the hypotheses are met, either this hypothesis or this one. So one of the things we would like you to understand, and hence the reason I wrote this in red, is that you can't just use L'Hopital anytime you want. You have to have a certain scenario where it applies. Does that make sense? Yeah, so I mean, I would not, you're not going to get 0 points if you don't write it, but I would, you know, I encourage you to know when you're using L'Hopital and when you're not. I mean, that's the stuff you take with you when you leave this class. I mean, again, 10 years from now, I doubt any of you are going to be using L'Hopital's rule. You're probably not going to be doing calculus. However, understanding how to justify things is something that you can take with you in life, not just in math class, right? Why is something true? I mean, you writing L here and justifying why this line is logically sound and true is no different than you when you're writing an English paper justifying a point with evidence, right? I mean, you're providing evidence of something. Okay. Anyhow, that's a good question, and I would not, you know, you depends on what kind of mood I'm in. You probably win these points. So let's explain why this sort of works, and I think you should, you know, I would encourage you to try to make sense of this. So sketch of why L'Hopital works. So so recall that f of x is approximately its tangent line, which is f of a plus f prime of a times x minus a. And again, this is its tangent line, or its linear approximation. And of course, g of x has a very similar that should be g. And this is also its linear approximation. So maybe I'll write this in red. So what does this mean? Well, this means that if you take the ratio of f over g, then you can write down their approximations. But here's the catch. Here's the catch. If you look at the assumption here of L'Hopital's theorem, when we say, for example, that f over g is 0 over 0, well, that means you're just plugging in a here and you get 0, and g here and you get 0, right? And so that is equivalent, you know, hand-waving equivalent, if you'd like, to the fact that this is equal to 0 and this is equal to 0. So then we can put that in there, and then you're left with f prime of a times x minus a over g prime of a over x minus a. And then, of course, x minus a is in both the top and the bottom, so that cancels and that cancels. Cancel common factors, and you're left with, as L'Hopital suggests, f prime of a over g prime of a. Now, there's some technicalities that you'd have to be careful of, but this is the gist of why what we did works. I have a question about this. Again, am I going to ask you to prove this in a test? No. What I wanted to do is I like to give you this little sketch because I hope you think about it and how it sort of gives light to why L'Hopital's rule works. Okay. Cool fact about L'Hopital that's very useful as well. So it also works for the limit as we go to plus or minus infinity. So let's look at an example that's familiar. So let's take the limit as x goes to infinity of x plus 5 over 3x plus 2. Now, we studied these types of limits before, and you should know at this point that this limit is 1/3. And the reason this limit's 1/3 is because the degree of both of these leading terms is 1. And so it's the coefficient. But L'Hopital says that you can take the derivative of each piece and so the derivative of the numerator is 1, the derivative of the denominator is 3, and so you get 1/3. Not that you would necessarily compute this limit that way, but you could if you wanted. So again, this is a new tool. You can't. It doesn't always apply, but it applies sometimes. Sometimes you have to use L'Hopital's rule more than once. Before we do another example, does anybody have a question? Comment? Once. All right, so L'Hopital also helps with what we'd say complicated limits. So here's a famous one. The limit is x approaches 0 from the right of x times the natural log of x. Now, why am I putting this plus sign here? Well, remember, the log is not defined for negative numbers, so I'm just being sort of overly cautious. So here's the thing. So the first thing you note is if we do a direct evaluation, gives 0 times log of 0, which is 0 times negative infinity, whatever that means. And what you need to understand is this does not fit, so to speak, the hypothesis of L'Hopital's rule. So what we need to do is we need to note that in this situation, that doesn't mean all is bad. That just means we have to think of the problem from a different perspective. And so what I can do is I can rewrite. So the key observation is to rewrite. So here's what we're going to do. So you can write x log x as log of x divided by 1 over x. That is a very elementary fact. Now, the hypothesis of L'Hopital's rule is met. What do I mean by that? I mean that if you plug 0 in for x, you get infinity over infinity. Log of 0 over 1 over 0 is, I know this doesn't make sense, but you get negative infinity over infinity. So now we can apply L'Hopital's rule if we do it properly. By the way, this trick of rewriting something so that L'Hopital applies is not really a trick. It's called a method because it works lots of times. It's not a magic trick, it's a method. Okay, so what can we do? So we can now take the limit. The limit is x goes to 0 from the right of x log x. By basic algebra, it's the same as this. And by L'Hopital's, we can take derivatives. And so the derivative of the numerator is 1 over x. The derivative of the denominator is negative 1 over x squared. And this simplifies using 5th grade arithmetic. This simplifies to just negative x. And so the limit is 0. So you might not recognize that this simplifies as quickly as I do. That's to be understood. But what did you learn in like 5th grade? If you have a fraction over a fraction, you multiply by the reciprocal of the denominator. So this is 1 over x times x squared over 1, and you're left with x. 5th grade, 5th grade, 5th grade. You're going to say, I don't remember that. Absolutely. That's 5th grade. I'll ask Amy. She's a 5th grade teacher. Let's text her right now. We're going to ask her before, and then if you have any questions. It's multiplying and dividing fractions. 5th grade. Let's see what she says. How about this? This is funny. The only reason I shouldn't even say this out loud. This is very embarrassing. I know what we'll do. We'll mute so the people at home can't hear. All right. Do you guys have any questions about this? So why is this a famous example? Well, because this sort of idea is used in many important limits. So the above limit and the method we used shows up in many places. So here's an example. Before we do it though, there's another famous limit. We want to compute the limit as x approaches 0 of x to the power x. And once again, to be completely non-crazy, we'll do from the right. So we don't have to worry about negative roots or whatever the heck that might mean. All positive numbers. Now, the trick we're going to show you works in all kinds of places. So it ain't a trick. It's a method. It's a useful tool. So whenever you have, and this is very interesting, if you look at this particular expression, notice we have a variable downstairs and upstairs. So the variable is not only in the exponent, but it's also in the base. This is different than a polynomial, and this is different than an exponential function. The variable is raised to a variable. So here's a useful observation is you first need to note. First note that x to the power x can be rewritten as e to the natural log of x to the power x. Now you're going to say, why would I make it uglier? Well, the reason we're going to make it uglier is because the properties of log allow me to pull that x out front. So one of the properties of the logarithm is that if you have a log of something raised to a power, you can actually pull that power out front. Again, this is something that whenever you first learn logarithms and exponents, this is a fact that you should have been, you definitely learned it. It's just the problem is you probably have forgotten it. Here I am to remind you of this rule. Now, why is this useful property? Not only did I introduce E, so why is this true? First off, E and the log are inverses. So if I take E to the log, they're just undoing each other. But by doing this, it allows me to get that X out of the exponent. So another basic fact of, and this is worth noting, so these are basic facts of logs. And I'm not saying basic to offend you, but these are things you should know. You should know that E to the log of star is always just star. Whatever's inside, it doesn't matter. As long as it's well defined. I mean, you can't take the log of a negative number. And then also, you know that the log of A raised to the power B is just B log of A. So these are things that we're using these to get our expression in a workable place. And so now we can put the pieces to our puzzle together. Yep, even Amy said they do that. Multiplying and dividing fractions is 5th grade math. There you go. That'll make you feel bad for the day. Isn't it mean when like people say, you remember learning this? Like, I hate when people assume we don't forget things, right? I understand you forget things. I forget things too. All right, so here we go. We can put the pieces to the puzzle together. So we conclude that the limit as x approaches 0 from the right of x to the power x, that is the limit as x approaches 0 from the right of e to the x log x. Now, the exponential function, here's another bit that we sort of, you don't appreciate when you were in learning, when we were learning about continuity. The exponential function is a continuous function, which means you can take that limit upstairs. But we already found that that limit was 0, so we get e to the 0, which is 1. So this limit is also 1. Scary as it is. Now this is a hard, this is not an easy problem. This is one that will take some time if you're trying to actually learn it. All right, so ponder it. It's scary. We're out of time. Any questions, comments? Good news, on Tuesday, we start area and hence integration. All right, guys, have a good weekend. Thank you very much. If you have questions, please email me. Don't forget, I should